Two other types of rotary pumps use gears to move fluid. One is an external gear pump, and the other is an internal gear pump. Some rotary pumps use vanes instead of gears or lobes to positively displace fluid. An example is this sliding vane pump. It has vanes that can slide in and out of the rotor. A rotary positive displacement pump uses the rotating motion of components such as screws, gears, lobes, and vanes to move fluid. In this part, we'll look at several examples of rotary pumps. One common type of rotary pump is a single screw or progressive cavity pump. The screw or rotor is located inside a casing, and it's connected to a driver. As the screw rotates, cavities form between the casing and the screw. These cavities move or progress toward the pump's discharge as the screw rotates, carrying the fluid along. Progressive cavity pumps are especially useful for moving extremely thick fluids, such as sludges and gels, since they can move these fluids without clogging. Another type of screw pump is the two-screw pump that's represented here. One of the screws is attached to a shaft that is coupled to the pump's driver. This screw is the driver screw. It's sometimes called the power screw. Power is transmitted from the driver screw to the other screw, which is the idler screw, through a set of timing gears. Fluid that enters the pump is directed toward both ends of the casing and is trapped between the casing and the screws as the screws rotate. The fluid is moved from both ends of the pump toward the center, which is also the pump's discharge. The force that is exerted by the rotating screws pushes the fluid out of the pump and through the discharge piping.
Working principles of a fixed displacement piston pump. The device we're going to describe here can also be used as a hydraulic motor. A main shaft connected to a gasoline engine or an electric motor rotates a cylinder barrel. The cylinder barrel looks like a revolver's barrel, and the pistons are located inside this barrel just like bullets. The rotation of the barrel forces the pistons to rotate with the barrel. The round ends of the pistons are connected to the yellow shoes, which slide on an inclined black swash plate. Springs in the cylinder barrel, which are not shown in this animation, forces the pistons towards the swash plate. Let's observe the motion of one piston inside the cylinder barrel. Notice that during one revolution, the piston moves inside the cylinder barrel from the top left to the bottom right, and back to the starting point. The horizontal distance between the top left and bottom right are fixed, and thus the name of the pump, fixed displacement pump, is derived from this fact. While the round end of the piston rests on the yellow shoe, which is sliding on the black swash plate, the other end moves closer to the green port plate during half of the rotation, and moves away from the green port plate during the other half of the rotation. The view of this port plate is shown as if an observer is looking at the pump parallel to the rotating shaft from the yellow port location. As you can see, there are two crescent-shaped gaps on this plate that are shown by the red and blue colors. The red indicates the high-pressured oil, and the blue indicates the low-pressured oil. The same color convention is true for the oil inside the cylinder. Notice that for the high-pressured oil, the pistons move toward the port plate and force the hydraulic oil into the red crescent gap on the port plate. The movement of the oil in the crescents is shown with the white bubbles. For high-pressured oil, the bubbles move toward the exit port, indicating that the oil is coming from the cylinders. For low-pressured oil, the bubbles move away from the inlet port, indicating that the oil is coming from the outside. The oil in the blue crescent is sucked in by the pistons moving away from the port plate. After a cylinder reaches its furthest point from the port plate, the cylinder passes the gap between the crescents and the compression cycle starts. Let's see how two pistons operate. Notice that during compression, the piston passes in front of the shaft, and while replenishing with fresh oil, the piston passes behind the shaft. This was done to show the 3D visualization of the pump. And here are all the pistons working in harmony. In practice, the number of pistons are usually odd numbers, such as 7, 9, or 11. In this animation, we're using 6 pistons to make it easier to animate. By looking at this animation, observing the motion of the pistons, and our color code convention, we can immediately say that the system is working as a pump or a motor. For the pump, the piston moves toward the green port plate when the cylinder color is red, and away from the port plate when the cylinder color is blue, and the opposite is true for the motor. This is also shown on the port plate disc on the right. The red circles ride on the red crescent, and the blue circles ride on the blue crescent. The opposite is never true. In future videos, we will represent hydraulic circuits and motors with the green port plate, disc shown on the right. But how can we tell whether a port plate disc represents a pump or a motor just by looking at it? Unfortunately, we can't, since we don't know whether the piston is moving toward the port plate or not. To overcome this, let's make one more convention. When the colors of the discs are lighter, the piston is closer to the port plate, as shown in this section of the animation. And if the colors of the discs are darker, the piston is away from the port plate, as shown in this section of the animation. This is how we can tell whether the port plate shown represents a pump or a motor. Since the red discs on the red crescent changes from a deep red to a lighter red, this signifies a pump. If it were a motor, the opposite would be true. This concludes our presentation on the fixed displacement piston pump. We will show an advanced version of this pump, the variable displacement piston pump, in one of our next videos to come.
Components. External components are visible. Internal ones aren't until the pump is drained and disassembled. Centrifugal pumps have 6 main internal components: the pump shaft, the impeller, wear rings, the volute, packing or mechanical seals, and bearings. The internal parts of a centrifugal pump are mounted on the pump shaft. It's a single piece of metal that's been machined to fit the pump perfectly. The shaft is usually made of stainless steel or some other corrosive resistant material. And for a very practical reason, replacing broken or worn-out shafts is expensive. Some pumps have a shaft sleeve, or metal cylinder that fits over the shaft and protects it from damage. It's easier and cheaper to replace this sleeve than the shaft itself. This circular device is an impeller. The impeller fits snugly on the shaft and is usually pressed on. It can be held in place by several methods, but the most common is with a key and keyway. The impeller is the most critical part of a centrifugal pump. Why? Because its size and shape and the speed at which it turns determine pump capacity. There are 3 types of impellers: open, semi-open, and closed. Open impellers basically are vanes mounted on a shaft with just enough backing or shroud to keep the vanes rigid. Semi-open impellers are completely covered on one side of the vanes. Closed impellers have shrouds covering both sides of the vanes. They also have a central hole or eye on one or both sides. That hole lets fluid enter the impeller. Impellers are also classified as single or double suction. With single suction impellers, fluid can enter only one of the impeller's sides. That can cause problems such as imbalancing thrusts in the direction of the suction. In high volume or high discharge pressure pumps, that problem can be serious. It's resolved by using a double suction impeller. This type lets fluid enter both sides of the impeller. That makes the thrust generated on one side of the impeller counter the thrust from the other side. Pumps also come in stages, single or multiple.
Axial pumps move fluid in a straight line. Most axial pumps are located at an elbow in the piping system. A drive shaft extends into the process flow with a propeller attached to the end. When the propeller turns, the blades pull the fluid down the shaft line.